Hello everyone, welcome to today's webinar. And today my topic is talking about the software and hardware tools you can use for your deep learning research on SHARCNet. So today's outlines, I will cover the very brief introduction to the deep learning, and also I will introduce you some new hardwares in SHARCNet to do the research. And also I will show you some demos of how to use the most popular software tools. And at the last, I will discuss some common issues you should consider about when you're doing your research on SHARCNet. Okay, so the deep learning, you must be familiar with the word deep learning because people are talking about deep learning every day these days. So deep learning is learning deep. So what is deep? So deep means multiple layers. Or at first the people believe that deep learning is learning deep neural networks, but now in general that way people talk the deep learning is to learn multiple layers of representation. So the corresponding to the different level of abstraction. So each layer of the neural network or each layer of the convolutional neural network is different levels of abstraction of features. So deep learning theory came out in 1980s and 1990s, but after that, people developed these theories to make it work with the deep neural networks. So deep learning is also exploiting composition, giving us an exponential gain in representative power because our human organize ideas and a concept hierarchically. And deep learning also gets some biologically inspired because the brain is deep. Alright, here I'll show you some deep learning successes. So first is well-known thing is the vision. So the vision is you can find the people doing object recognition and detection using deep learning. Also some post-estimation and active recognition. People also use deep learning for speech and natural languages recognition. And recently, some people using deep learning technology for gaming. And you must have heard about the news that Google used the deep learning technology to master the game of Go. When talking about deep learning, the first thing that came into my mind is the ImageNet challenge. It's a large-scale visual recognition challenge. So the ImageNet is kind of benchmarking object category classification and detection on hundreds of object categories and millions of images. So actually, this computation is for 1,000 object classes, and approximately there was 1.2 million training images. Well, ImageNet is very important because it's considered to be the first real benchmark where deep learning beats sophisticated computer vision system. You can take a look at this. So in 2010, for ImageNet computation, people can only have around 30% top 5 error rates. But nowadays, in 2015 challenge, that people reached 3.5% top 5 error rate. Our human brain, it is believed to can only have 5%. So the deep learning technology, computers with deep learning technology that overcome human beings. Okay, so deep learning with high performance computing. So deep learning is particularly well suited to parallelization, and there are two kind of parallelization strategy. The first one is data parallelism. So it's in the pixel-based input like images and videos. So people use multi-core CPUs or multi-GPUs to respond for a chunk of input data and put the result together somehow and to calculate the final results. Another strategy for this is to do the task parallelism, and you can split your model into two or multiple pieces, use each CPU cores or GPU to sponsor part of the model architecture. And thanks to the development for the accelerators like GPUs and FPGAs, so Theano, Caffe, and some other tools all provide GPU support by way of CUDA. And also you can find some other libraries that support OpenCL or have some support on FPGA. Also, you can find the tools like Nvidia DIGITS that provides you multi-GPU support, and even for distributed framework. And Google just recently open sourced their distributed version of TensorFlow. That means you can run your deep learning research on the HPC cluster. Okay, so the HPC cluster in SHARCNet, you, you may remember that when you attend the new user seminar, and we told you that the biggest GPU system we have is Monk, and we also have some other contributed GPU cluster. But our Monk cluster is relatively old, and it is not really a good cluster to do deep learning research because the GPU is a few generations behind. But now we have some contributed newer GPU cluster. So the first one is called Mosaic, which has 20 GPU nodes, 1K20 per node, and each node has 20 CPU cores with 256 memory. And all these 20 nodes are connected with the InfiniBand QDR networking. And it also provides you a development node called MOS1, so you can do some development work on that. And we will have another GPU cluster open soon. It is called Copper, which has 8 GPU per node. So there are 4 K80 cards per node. In total, there is 8 GPU units. So 16 CPU cores with 96 gig memory and connected with the InfiniBand FDR. You have to notice that all these two clusters are contributor clusters. So if you are not one from the contributor group, you have 4-hour running limitation. Okay, so some popular tools for deep learning research these days. I believe the most popular tool nowadays is the Google TensorFlow. It's a Python-based tools. And we have a website talking about the TensorFlow. I will show you later. So some other popular tools are Caffe and Nvidia DIGITS. So the reason why I put Nvidia DIGITS together with Caffe is Nvidia DIGITS use Caffe as backend, but it supports multi-GPU. And I will show this too later. And others like Theano, PyLearn 2, and Lassagin is all Python-based. They are all based on Theano. And Theano is very easy to use, and I will give you some demos of these softwares. Okay, so if you go to the SHARCNet help wiki, so you go into the help wiki, if you search TensorFlow, you will find a page about the TensorFlow. So in this page, there are 2 parts. So the first part is how to run TensorFlow. So you can see the title is Testing TensorFlow because we haven't made TensorFlow as a modular, so you have to do some manually setup to run TensorFlow. So we got TensorFlow 071 with CUDA 7.5 and the CUDA in 3rd generation on Mosaic and Copper. So you can find the details of how to run this on the cluster environment. And I also have the instructions on building TensorFlow. So it's quite complicated, but if you follow the instruction one by one, and you can get your own TensorFlow. Okay, so TensorFlow is the first software tool I want to show you. So let me just switch to the terminal window. Okay, so for example, we log into Mosaic. Once we log into Mosaic, we stay on the login node. And if you go to the OPT SHARCNet testing folder, in this folder, I get something related to the deep learning. So you will find the cuDNN, different versions, and the TensorFlow directory. And the TensorFlow build is the TensorFlow source code and the modify the make files. And I also got Caffe, Nvidia DIGITS. So if you go inside the TensorFlow, so you will find a whale file here. Because TensorFlow is kind of Python package. To get TensorFlow installed, you can use the pip install and then put it into your user folder. So if you don't have a pip or updated version of pip, you go for the website, and in the TensorFlow website, I have detailed instruction on how to get a newer pip. So once you get the pip ready, you just run pip install. So you got this. So you find your pip and the pip install, and find my TensorFlow whale file. So -- user means it will be installing under your user environment. So it will be put inside your home directory. So okay, so once you got the TensorFlow installed, so that basically means that you have TensorFlow as a Python package, so you have to use Python to run the TensorFlow. But before you run the Python, you do a modular check. So you will see that when you do the modular list, you will see the default modular on SHARCNet. It's relatively older modulars. To run this newer software tools, you have to load the newer modulars. So I will show you the modulars you need to load. So the first thing, we want to unload the Intel modular and load the newer Intel, load the newer OpenMPI, and load the HDF and the Python. So the most important modular here is our newer Python modular. So once you upload all these Python modulars, that you can run the TensorFlow, because my TensorFlow is built against this newer version of Python. So you have to load the Python modular to use this Python to launch TensorFlow. And cuDNN is Nvidia's deep neural network library, and it will provide you the fastest speed for training neural network. So if you want a TensorFlow to use the cuDNN library, you have to export the path, the LD library path, to tell the TensorFlow where to find the cuDNN. So here I'm using cuDNN version 3 because I built my TensorFlow against the cuDNN 3. So I have to export this environment. After you got all this ready, and you can submit the job. So let me show you a very easy example in TensorFlow file. So in TensorFlow, maybe I will go to my TensorFlow folder. So there are some models in TensorFlow source code. So I go for one of this model, CRF10. So in this model, you will find the data folder and the training folder. This folder doesn't exist if you just download the source code, and you have to generate this folder using the script to get the data. But it will be very easy when you run the script, and it will download the data from the internet, and it will generate this to folders. And these two folders is very important because you have to specify the training DIR and the data DIR to run this job. Okay, running TensorFlow, I can do, let me show you an easy example on the development node. So I go to the development node. So it's most one is a development node that you can run your job interactively on this. Once you log into the development node, you have to do the modular load again and export the path. So I export the path, then let's try which Python. Yeah, it's using the newer Python module. So let me go to the TensorFlow folder. So to run TensorFlow, so when you get the data ready, when you get the script, it's a Python script ready, so you can just test your script on the logging node. So I'm testing the CRF10 training Pi, and I would specify the train DIR. Equals I'll put these two flags. These two flags are required because in this Python script, it will all depends on how you write this Python script. So you can put an extra flag to specify where to find the data. Okay, so let me run it to you. So when you run the TensorFlow, it will do some system check first. Firstly, they check if you have CUDA ready and if you have CUDA DNN ready. And also it will give you some information about the GPU card you're using now. And after that, they were doing calculations. So you will see now we're doing the training the neural network. Okay, so I will just queue this job and show you how to submit the job to the scheduler, because there is only one development node. You're not going to run all the whole training on the development node. So you have to submit that as a job to the scheduler. So to submit the job to the scheduler, you do SQ sub, and it put a queue to the GPU queue. Because TensorFlow is not a single thread GPU work, it's the multi-thread. So it is better to specify the threaded model. So you use the threaded, and you give them like whatever, you give them like 2, and you specify the GPU, how many GPUs you're going to use is 1, and also the memory you're going to use, because Mosaic cluster is the memory is very big, so I can specify, okay, I want a 100 gig memory. And the running time, because I'm not from the contributor group, so I can only have 4 hours running limitation, so I can only specify 4 hours. But it's not a problem because most of the deep learning tool provide you a snapshot and a checkpoint. So you can snapshot and resume your work after 4 hours. So I'll put a -O. Okay, called TensorFlow. And I'll put the Python command after that. Okay, so now I successfully submit the job to the scheduler. Let's check with the SQ sub. Okay, so you will see there was one job running on mode 7. So let's take a look at the output file. Okay, in the output file, they passed all the tests, and it's running now. Okay, Randy. So that is how we run the TensorFlow. It's very easy, and you can do some development writing TensorFlow script on the development node if you find it's working and you submit a longer job to the scheduler. And TensorFlow also support multi-GPU training. After we open Copper, you can submit a GPU job on the Copper node and to accelerate your training process. The second tool I want to introduce is the Nvidia DIGITS. So Nvidia DIGITS is a website-based training tools. So you got a website interface. It will be very easy to use, and you can see all the sightings and just by clicking on the website. Okay, so this is an Nvidia DIGITS wiki page on SHARCNet Help Wiki. So basically, when we run Nvidia DIGITS, we want to keep keep a copy of it because all your job. Because I put it into the OPT SHARCNet testing folder, but you are not allowed to read this folder. But Nvidia DIGITS will keep all the job information under the folder, so you must have one copy of this folder under your file system, under your directory, and then you create a job and run your job there. So the first thing is you follow this line and to put it somewhere under your folder. And set the environment, and I will show you how to set the environment and submit the job. So for setting you have to set the modular and the path to make sure that the system can find where the Nvidia digit is. So the easiest way to do this is I have a script. It's called site digits. So in this script, it will automatically unload the modular and load the modular that needed. And you can do a source this script, and it will set automatically for you. If you do a modular list, you can see I've already switched all the modular to the one I used to build the Nvidia DIGITS. Okay, I will directly show you how to submit it. You can run Nvidia DIGITS server on the development node, and you can also just submit this job to the scheduler. So once you got a copy of Nvidia DIGITS, you go inside in this folder. So in Nvidia DIGITS, this is a 3.0 version. You will find a DIGITS server. It's a script. And to use this Nvidia DIGITS, we only need to submit this script to the scheduler. Okay, let me show you. We do the same thing using the SQ sub to put it into the GPU queue to give it at least 2 threads and asking for 1 GPU because there was only 1 GPU per node. And we can also have 100 gig. And we specify the output, specify the running time, and we just submit this server to the scheduler. Okay, so it's running almost 19. So server is running there, so how can we connect to the server? After you submit the job, you use the SQ jobs to check where your job is running. So now we know, okay, so it's running almost 19. So how can we connect to this? And before you log in, let me log on. Before you log into Mosaic, you have to put -y flag. So here -y flag will enable the X11 window forwarding because you're going to use the browser. And you're not able to use the browser on your desktop to connect it to the compute node, but you can use the browser on the login node to connect to the compute node. So you have to log into the login node with the -y, and you can download some web browser. I download this Firefox here. So then I'm running a Firefox to put it into the background, and I will open the XE11 window with the Firefox. All right, so this Firefox window is open on the login node. So how to connect to the DIGITS server? So we remember that the DIGITS is running on MOS 19. So there was a port, it's 34448, it's a default port. So we put the MOS 19 default port, and then we're going to the DIGITS that is running on MOS 19. In this homepage, you will see some information about how many GPUs are available here. Because it's on Mosaic, I'm asking only one. If it's on Copper, there will be 8 GPU available showing here. So to use the Nvidia DIGITS, the first thing you have to prepare the data set. So the data set can be image and it can be others. So we have a classification. For example, if you have your own copy, you won't see all this job information here because this is on my folder. So you will see an empty here, and then you start from creating the data set. So in this folder, you specify the type of the images, and you can use the text file. It's the label files to which it's a similar thing on Caffe. You can find the information on how to create these label files on the internet, on Nvidia's internet. So you got the labels ready, and you got the file location ready, and then you create the DB backend as a LMDB as the default and the suggested one. Then you click create, and it will probably run a job. And I have already got one job down here. It's called ImageNet. So let's go inside to take a look what's inside this data. So after you create this, it will show you the image. So how many images inside is like 1.2 million images here, and the size of the data set, and they calculate the image mean, and also the validation data set is here. So let me show you a very simple example to train the AlexNet on this ImageNet data set. So you go to the model, and you create a classification model here, and select the data set ImageNet, and you can do crop. So crop for AlexNet, the cropping is 227. And here you will see there are 3 default networks. So you can click AlexNet, and you can also customize it. And Nvidia DIGITS also provides the visualization functions. Then you can see how the neural network looks like. Okay, so we go back to the standard, click AlexNet, and then we set up a batch size at 128. And you can define the learning rate, you can define the snapshot interval, and you can also have some advanced learning rate options. Okay, give him a model name, test 2. Okay, then you just click create. And in this page, you will see the data set, the GPU usage. So there is 1K80 running here, the memory usage and GPU utilization. And if you go to the node you're running, this is the MOS 19. So you SSH to MOS 19, and you can see Nvidia DIGITS is using Caffe as the backend, so it's running there. So you can see a Caffe process. Yeah, in this terminal window, so you SSH to MOS 19, and you will see all the processes you are running on MOS 19. There was a Caffe process because the DIGITS using Caffe as a backend actually is a multi-GPU version of Caffe. All right, so the next important tool I want to introduce is Caffe itself. So a lot of people want to just use Caffe and not use the Nvidia DIGITS, because some people doing development work on Caffe, they have their own modification on it. So let me switch to the Caffe page. Okay, in this Caffe page, I got basically two important sections here. The first one is how to run Caffe. It's running Caffe. The next one is how to build your own Caffe. So today I'm not going to cover how to build Caffe because it's relatively complicated. I will only show you how to run a pre-compiled Caffe on SHARCNet. So running Caffe, you still need to set the modular ready and set the Caffe root, set the path, LD path, and also the Caffe has the Python wrapper, so you can use the Caffe's Python wrapper. Then you have to export the Python path to point it to the extra Caffe libraries. So I also have an easy script for doing all this. I put it into the SHARCNet testing Caffe. So let's do it on the terminal window. Okay, so here, for example, I'm using MOS1 as example. So I log into MOS1, the development node, and then I do source this script, so they will set up the modular automatically and set up all the paths. If you check where the Caffe root is, so you do an echo. So echo Caffe root. So this one is the precompiled one on SHARCNet OPT SHARCNet testing folder. So running Caffe is similar with running the digits. So you have to build the LMDB dataset first. So I'm not going to show you how to build it because you can follow one simple script in Caffe to build the LMDB dataset. Today I'm only going to show you how to define or modify a model and how to run this model on the dataset you have. So let me show you the dataset first. So I got an ImageNet dataset here. So I got training LMDB and I got a validation LMDB. So to run Caffe, you have to get these two LMDB dataset ready, and you also have to get the image mean calculated by the image mean script. Once you run that script, you get the image mean. So you also have to define your model. So let's go inside to this example. It's the BVLC AlexNet model. So in this folder, you got a solver. You got a train validation prototext. So the solver prototext. So let's go inside to take a detailed look at the solver. So in the solver prototext file, you have to define where your neural network is. So it's the location that the train validation prototext file. And you define all the parameters like a test iteration, you got the learning rate policy, you got the base learning rate, and the snapshot folder, and also the server mode must be GPU. So in the train and validation prototext file, if you just get this file online from somewhere else, you have to modify this file based on the dataset location. And the first thing you have to modify is the main file. Where is the main file? So this is the path to my main file. And you also have to modify the source for the data, for the training data. And also the backend is LMDB, and the batch size. You also have to modify the source to the validation data to where you put the dataset. After you set this all down, and you can just test the job. So we can run a very easy test job. So the Caffe. So for example, if we are on in the login node, so this is where Caffe main program is. So it's under Caffe root build tools Caffe Bing. So if you want to train a job, so you just say, okay, Caffe Bing train, and you specify the solver. The solver is the solver portal text file, and you can run it directly on the login node. So you will see the Caffe is running. Okay, so I will just stop this and show you how to submit the job. Well, submit the Caffe job, you just submit this command to the scheduler. And let me add SQ sub in front of it. So you submit to the GPU queue and give Caffe 2 threads. And running time like 4 hours. And the GPU 1, and you got MPP equals 100 gig. And you also have to specify the output. And you submit the job. Okay, now you see the Caffe is running on MOS 20. So if you take a look at the output file, it should show the similar. Yeah, it should show the similar output here. So that's the basic way to run Caffe. Okay, so running Theano will be very easy because our Python modular has Theano built inside. So if you check, once you load the Python modular, the newer Python modular, this one, when you just run Python and you try to import Theano, it's there. So running Theano will be similar to running TensorFlow because they are all Python-based packages. So now you load this Theano modular and you can do whatever you want to do this. Okay, running Theano is very easy. I also got a Theano page talking about how to build your own Theano and how to run Theano on SHARCNet. Okay, so the page is here. So SHARCNet installation. And I also talk about the cuDNN environment because you have to set the cuDNN path so Theano can find cuDNN to accelerate the computation. And Theano can be used on some other cluster like Monk and Andrew. It hasn't to be Mosaic and Copper. All right, so these tools are basically all the tools I want to introduce today. So our next topic is about the common issues. So the first issues, as you may notice before, I gave them all 2 cores when I submit the job, but actually when you submit TensorFlow needs some extra cores, CPU cores, to do some pre-processing and loading the data. So usually it will take around 5 CPU cores to do all this job. So when you submit the TensorFlow job to the scheduler, you'd better ask 5 cores or more. So for digits, you'd better ask for the whole node because, well, training a neural network using digits may only need like a few cores, like 3 or 4 cores. But when you use the digits to prepare the data set, it probably used up all the CPU resource because it can do a parallel, like preparing the data. So it will give you a faster speed if you have more cores. So when you submit a digits job, you probably ask for the whole node, all the cores on the node. Caffe can use like 2 cores, one for training, another one for loading and pre-processing the data. If you submit Theano, Well, it depends on what if you are using other Python package. Well, Theano itself, I mean training, if you're training with Theano, Theano itself uses only one core because Python doesn't support multi-thread. But if in your Theano code it contains some NumPy or SunPy operations, NumPy is built against to MKL, it can take advantages with multi-cores. So if you're using NumPy to do some preparing the data or pre-processing, and you'd better ask for more CPU cores. And the choice of GPU, so Mosaic has K20, and it has one limitation. The biggest limitation is the size of the memory. If you are training a relatively small network like AlexNet, you probably 5 gigabytes is probably enough for you. But if you are trying to run a large model like a GoogleNet or VGG model, you probably need more memory. Once we got Copper ready, open to the public, you can use Copper because it has around 12 gigabytes memory. Well, if your model is very small and your data set is very small, and you don't want to wait for a long time in the queue, and maybe another better place to go is Android that has 750 Ti GPU, but the memory is very little. So if you are very new to Theano or if you are very new to Caffe, your model is very small, and you can try there first because that cluster is very empty. Okay, so the next big problem is the file I/O. So when you do this deep learning research, you have to prepare your data. Caffe, DIGITS, and Tensorflow, they all requires. It's not a requirement. It would be better if you put all this image together into a single file. They call it LMDB data file. So Caffe and the DIGITS will get the best performance when reading the data from the database. So to get the database ready, you have to get the ImageNet, like images or other input items. So all these images are small, and you'd better put them into the temp. Temp is the local attached storage. So each node has their own temp. So if you want to do the pre-processing and to prepare in the data file, and you'd better use the temp to get the best performance because your home and work directory are remote. So all the files have to go through the internet to get into the cluster. So it will be very slow when you are handling with the small files. But once the database file has been created, you can keep the database file, because the database file may be very large, so you can keep that into Scratch or Work. And then you will Scratch, or sometimes Scratch will give you a better performance, but sometimes Work will give you a better performance. So you can, if you have any I/O issues, you try a different location. If you put the data into Work and you find there are a long waiting time, that Caffe will show you, and you'd better to keep a copy on Scratch and try to read the file from the Scratch. So the internet access problem. Well, some deep learning tools like TensorFlow, so you got some script from TensorFlow. Within that script, some scripts are trying to access the internet to get the data file download. So that means you cannot submit the script that contains the internet access to the compute node because only the login node has internet access. If you submit the job to the compute node, that in this script you have internet access requirement that will fill this job. So it will be better in your script you can separate two scripts. One script is to get the data ready. Another script is do the real calculation training part. So you run the first script on the login node to download the data, and then run the training script on the compute node to submit them as a job to the compute node. So that's the very important thing that you have to keep in mind. So the multi-GPU, as I mentioned before, the DIGITS support multi-GPU, and TensorFlow also support multi-GPU. DIGITS only support the shared memory model. So that means all the multiple GPUs have to be inside the single node. So Copper will be the only place that you can use DIGITS for multi-GPU training. And TensorFlow, newer TensorFlow support distributed training. Or you find some other people's framework that support distributed training, and then you can run this using MPI on both Copper and Mosaic. So one last important thing I want to mention here is the security problem. Well, it seems that Nvidia DIGITS is not designed to run on a public cluster environment. So when you run the Nvidia DIGITS server, it will open a port to public that will allow everyone can open the web browser using the job that you submit. So that means if you submit a job to the scheduler, for example, if it's on MOS 20, I can open my browser to connect to MOS 20 without any asking for permission. So you have to keep that in mind. That's another reason I want you to ask for a whole node, because only if you can log into the node to check the port, because you can change the port number. The default one, everybody knows the default one, but you can change that into some other numbers. And if you submit the job to the whole node, other people won't be able to log into the node to check which port is open. So people will not know the port you open on that node. So that will be a little bit better, but I'm not quite sure if people still can get the opening port information. But keep that in mind, that everyone can log in, can open the browser, access your server, DIGITS server on the node.